Since we have very useful weapon, which is general function type of Polya theorem, let's revise it for a moment. The permutation of combination over the blackboard. Over here, we still the same. We are trying to find for the regular hexahedron if we use 6 type of color to color it, where each face color is different. Under this situation, how many different painting spaces are there? Let's analyze it carefully. And this time we thought of using general function to solve it. The combination and permutation on the blackboard. First, the first step is to find out all the rotation group of the regular hexahedron. We are very familiar with it already. Just now we have already enumerated it for several times. Include fixed center to center, positive and negative 90-degree rotation, face center to face center rotate of 180 degree, edge center to edge center rotate of 180 degree, and also diagonal lines as a shifted axis and rotate the positive and negative 120 degree. And this time we just need to consider how does the corresponding permutation looks like. Then list all these generating function for us to analyze. Let's look at the first component corresponding general function. How should it be written? Over here it is a 1 cycle each. Therefore we use a variable represent respectively to replace use x1 to represent first color, x2 for the second until x6, and this time x1 plus x2 plus x3 until add up with x6, representing the coloring solution within the bracket. It contains total of 6, therefore it is to the power of 6, because face center to face center, all this permutation and the angle, after calculating this are total of 6. Therefore, correspondingly, it should be 6 multiplied by the general function of the expansion behind. Over here, 1 order cycle, x1 plus x2 continuously adding until x6 square, there is another one, contains 2 1 order cycle, which means quadratic component, contains 3 order cycle, and therefore it is x1 to the power of 4. Continuously adding until x2 to the power of 4, continuously adding until x3 to the power of 4, continuously adding until x6 to the power of 4, which is corresponding to this component, whereas face center to face center rotation of 180 degree. We have also the total of 3. Each component corresponding one is 1 order cycle. There are 2 order cycles. In the following, we will have 4 6 2 order cycle. Contains 3 this kind of situations. Therefore 6 multiplied by 2 order cycle, there are still 3. Add 8 multiplied by 3 order cycles, which contains 2. Then do not forget that you need to divide by the number of permutation, which is divided by 22. It will then structure regular hexahedron. The general function for the face coloring, what we are requiring? We are requiring each face is colored with 1 color and each face is colored with different colors. It simply means that x1, x2, x3, x4, x5, x6 may all be used. Because after having this kind of general function, the requested x1 multiplied by x2 multiplied by x3 until x6 is coefficient, we analyze them orderly. For each component inside, does it exist such a corresponding unit term? Let's analyze. Then we can see over the first component, we realize actually over here it will exist the x1, x2 until x6. Then it's corresponding after the expansion of 6 polynomial perform a non-stop permutation. The coefficient in front of 6 factorial, whereas behind it we will realize that over here after producing any of the components there is xk to the power of 4 always. Does not satisfy this kind of polynomial expansion. For this component there will be also quadratic component, but will not produce x1, x2, x6 until x6. Over here it is not possible to produce. Over here it is not possible to produce 2. To summarize, we will realize only the corresponding one this component will generate what we need. What we want, x1, x2, x3, x4, x5, x6. Therefore its coefficient is 6 factorial. Whereas at the same time, do not forget that we need to divide by 24. Therefore the obtained solution number is 6 factorial divided by 24 equal to 30. But again, it is using a different method to solve the combination and the permutation on the blackboard. Next, let's take a look at another question. It said that a regular tetrahedron, we want to paint 4 colors over its vertices, and at the same time paint the face with 3 colors, and at the same time color with 2 colors over the edge. Find the solution number. It's a bit different compared to the previous one. Just now it is just corresponding to certain several vertices, individually sealed them with beads coloring. or coloring the faces, or we can also color the edge. But over this question, we combine 3 of them all together. Then how are we going to do? Then similarly, our first step we need to analyze how many different permutations are there. Over here, to summarize, for regular tetrahedron, it is nothing more than vertices and the face center, positive, negative, 120 degree, and each edge center to edge center for flipping and no rotation. We list all the vertices, face, edge. When the vertices and the face center positive or negative 120 degree, the vertices is fixed and only 1 is the remaining 3 order cycles for faces. It is also the face is not moving, 3 faces performing a phase or performing a cycle. For edge, it is actually the cycle among the upper 3 edges. The bottom 3 edges are performing a cycle. Therefore, 3 order cycle contains 2. If edge center to the edge center perform an exchange for vertices, it is performing 2x2 exchange. Therefore, 2 order cycle contains 2. For face, actually it is also the exchange between the front and back, 2 order cycle. There are 2 for edge center. If you are considering its edge exchange, you will realize AB, this edge, because their direction is the same. Therefore, we still consider it a fixed. Whereas for ADBC, these 2 will perform an exchange. Therefore, 1 order cycle contains 2, where 2 order cycles contains 2. For example, for fixed permutation, we can see that there are 4 fixed point faces, whereas to edges there are 6. There are 6 edges which are not moving, and this time we can integrated them all together according to the law of step by step. Although there is 1 order cycle there, contains 3 order cycle, we can all use x to represent, mainly to differentiate them. We use x1 to represent 1 order cycle, x3 represents 3 order cycle. That's corresponding are all 1. Therefore, it's x1 to the power of 1, x3 to the power of 1. For faces, we use y to represent y1 contains 1, y3 contains 1. For edge, we use 2 to represent. In this 3 order cycle is these 3 quadratic component. For edge center to edge center, we also write it out. Then for corresponding edge center to edge center, because it is 2 order cycles, therefore it is x2 quadratic component multiplied by the quadratic component of y2. Because over here there are 2 corresponding different lengths of cycle, therefore we can use z1 squared multiplied by z2 squared. The edge center to edge center, it contains only total of 3, whereas the fixed image is respectively 1 order cycle contains 4. There are 4 order cycles, and 1 order cycle, and 1 order cycle contains 6, and this time there is only 1, and this time then only we integrate all the time together. First is rotation group, its permutation number is total 12, whereas its solution number, let's substitute it. And over there, x is representing how many colors. X is corresponding to 0.4 point is 4 coloring, because x1 and x3 should both use 4 to replace. It should be equal to 8, this type of permutation. Multiplied by this first component produce the power of 4. We can see that over this component it is the quadratic component of 4. Whereas over here, y1 and y2 are corresponding to the coloring of faces. It should be the quadratic component of 3. Over there, it should be corresponding to 2 colors coloring of these 3. It's the quadratic component of 2. Therefore, for this line, actually we can find out the corresponding element. The generation of counting is actually such a result. Similarly, we will realize over the edge. For edge ideal, inside it is a 4 color coloring, whereas y2 is corresponding to 3 color coloring, whereas they corresponding to 2 colors. Therefore, it is 2 to the power of 4, and at the same time, again, we can find out corresponding to it should be 4 squares multiplied by 3 squares multiplied by 2 to the power of 4. In front of, there are a total of 3. Whereas at the same time, let's look back. We will realize corresponding 1 order cycle should be 4 to the power of 4 multiplied by 3 to the power of 4 and 2 to the power of 6. Therefore, the last component is exactly 4 to the power of 4, 3 to the power of 8. 2 to the power of 6, we accumulate all the equation together, then divide it by 12, this kind of permutation, then we will manage to get an answer.